Let's pretend for a moment that we have two rocks, both of which contain a metal. The one on the left contains iron. I've drawn the iron in red, and the one on the right hand side contains potassium. Now there are many rocks that we can find in the Earth's core which do contain metals like this, and they can be a very useful source for us to actually obtain the metal and use it from its pure form. Now there is a term that we give this kind of rock, but before that there is one definition that we need to remember, and that is that we can only call this rock the ore, or we can only use the rock to obtain our metal if it is financially viable to obtain the pure product from the rock. So we always say, is it financially viable or cost effective to obtain the metal from the rock? And in the case of iron, the answer is yes, so we can put a tick. And therefore we call this rock iron ore, O-R-E, okay, iron ore. And so the definition of this is a rock in which it's financially viable or cost effective to obtain pure iron from it, or pure metal if you're talking in a more general case. On the other hand, potassium is not viable financially to obtain from rocks. There are various reasons for this, and the main one is that potassium is extremely reactive, and so therefore it's very hard to collect it from the rock. But it's important here to note that we won't call this rock potassium ore, even though it contains potassium, because it is not viable for us to obtain that potassium from the rock. And so what makes it financially viable to obtain the metal? Well, there are two main criteria really, and the number one is how easy it is to extract the metal from the ore. So how easy to extract the metal from the ore. And the second one is how much metal the ore actually contains. So how much of our metal the ore actually contains. That's because if it's easy to extract the metal, but there's barely any of it, then it's not going to be financially viable. There's no point for us because we're not going to get much metal out of it, even if producing the small amount of metal is relatively easy. So these two factors are very important. And it's important also to note that these factors can change, because if you think about it, not every rock is going to have the same amount of the metal, or it's not going to look exactly the same as another rock. For example, when you go gold mining, the usual thing to find is tiny little pieces of gold. However, sometimes you'll get lucky and you'll find large pieces of gold which can physically be taken away from the rock. That is extremely easy to extract, and it's also very cost effective, of course. However, if you have a tiny amount of gold in a massive rock, it's going to be way harder to get those tiny little pieces of gold out, and it's also going to be less cost effective because you are not obtaining the same amount of gold. So that's something to bear in mind. So the next logical question really is, how do we extract the metals? How do we obtain the metals from the rocks? So what we have here is called the reactivity series, and it tells us which metals in the periodic table are the most reactive and which ones are the least reactive. And so at the top here we have potassium. Now potassium metal is the most reactive metal in the periodic table, and as we go down we get slightly less reactive with sodium, calcium, and on and on and on. One important thing to note here is that we have carbon here in brackets, and in some tables you will also see hydrogen, which is down here between lead and copper. Now they're the only non-metals that you're going to find in the reactivity series, and there is a very good reason for that. When we find a metal in a rock, which we can call the ore, normally we will find it as the metal oxide, so it will be chemically bound to oxygen. For example, calcium oxide, you might have zinc oxide, you might have iron oxide, and so on. The important thing here is we can remove these metals depending on how reactive they are. We utilise a reaction which is known as a displacement reaction. Displacement reaction. Now you will have met this type of reaction before. What a displacement reaction is when a more reactive metal removes a less reactive metal from its compound. So it basically switches place. And the reason we've included carbon in this table here is that even though it's not a metal, it can take part in displacement reactions. And because carbon is relatively cheap for us and it's easy for us to use, we actually do use carbon to extract many of our metals. But as it's a displacement reaction, carbon will only work on metals which are found below carbon, so all of these. If we added carbon to calcium oxide here, nothing would happen because calcium is more reactive than carbon, and so carbon doesn't have the power to persuade, if you like, calcium to leave its oxide and for carbon to take its place. It's not reactive enough to do that. But if we have a look at zinc oxide, if we add carbon to it, elemental carbon, we will get a displacement reaction because carbon is more reactive than zinc, and so we'll produce zinc plus carbon has now become an oxide, and the most common oxide of carbon is carbon dioxide. You'll notice here that these aren't balanced, so what we need is 2 oxygens because we've got 2 oxygens in CO2, so we're going to need 2 of these. But if we have 2 of these, then we're also going to need 2 of our zinc metals to balance that. This is a displacement reaction which is used in the production of a pure metal, which is less reactive than carbon. Now there's another term for this which is often used, which is a reduction. This is an example of a reduction. What that actually means is that we have removed oxygen, because one definition of oxidation is the addition of oxygen, and the opposite of oxidation is always reduction. So oxidation would be adding oxygen and reduction would be removing oxygen. In this case, what we've reduced is the zinc, because the zinc has an oxygen bound to it on the left hand side. At the end of the reaction it doesn't, so we've removed the oxygen, reduced the zinc. If you wanted to speak about the carbon has therefore been oxidized. So carbon has now been joined up with oxygen, so it didn't have any oxygen on the left, does now on the right, and that is therefore an oxidation of carbon and a reduction of zinc. But as we are normally talking about the metals that we want to extract, they are reduced, so that is a reduction. Now this will work for most metal oxides where the metal is less reactive than carbon. So iron oxide, this will work, tin oxide, lead oxide, copper oxide, and so on. So if you are asked to write a balanced equation for the reduction of any of these metal oxides, then this is the sort of equation that you are going to be referring to. So that's a general rule, but how do we extract then these metals up here which are more reactive than carbon? So we're talking from potassium down to aluminium really. Well, the most common method with them is a method known as electrolysis. Electrolysis. Now the electro just means using electricity, and lysis means to split apart. So electrolysis. So why do we mean split apart? Normally we will have a salt or a compound of these metals. It is normally a salt. For example, sodium chloride. Sodium chloride is just table salt. Now if we want to extract pure sodium out of that, we can use the method of electrolysis. So it's important to note that this would have to be done with molten sodium chloride, because if it was a sodium chloride solution, then we'd also have water in there and we would end up with different products. And this is very hard to do. You're not going to be able to do this in a lab because molten sodium chloride is not a very nice substance to deal with. However, you get the idea, and using electrolysis we will be able to produce our metal. And so finally I'll show you a diagram of how electrolysis works. Now what we have here is a beaker which is set up with 2 electrodes. So these 2 rectangles here are electrodes. The one on the left is the positive and the one on the right is the negative. So the negative is here, and we call the negative electrode the cathode. And the left hand side is your positive electrode, which is known as the anode. Now let's pretend that we have molten sodium chloride in this beaker, NaCl. Okay. When it is a liquid, when it is molten, it will break apart into sodium and chloride ions. And these ions are free to move on their own. When we have a solid, they are stuck together too strongly by their electrostatic forces of attraction that we cannot break them apart, we cannot remove them from the crystals of salts that they're in unless we dissolve them. But here they're already split apart because we've done this at a very high temperature and they're molten. So let's say that this is a sodium plus ion and this is a chloride minus. We'll have loads of these, but we're only going to show one in the diagram. Now sodium has a positive charge on it, and you know that opposite charges attract, so sodium will be attracted to the cathode or the negative electrode. In this molten form, the sodium ions will travel towards the cathode and they will stick to the surface. Now the reason this negative electrode or the cathode is negative is because it will have a surplus of electrons. The sodium ions will take one of these electrons, and because they are positively charged, if they obtain an electron, they will become sodium atoms. And so a sodium ion plus a negative electron will give you a sodium atom. Now if this happens with millions and millions of sodium ions, you will get millions and millions of sodium atoms, and that is actually sodium metal. And that is what we are trying to produce. But just for completion, let's have a look at what happens to the chloride. Now the chloride is going to travel towards the positive electrode, or the anode, because chloride ions are negatively charged. Now when they get there, because the positive anode needs electrons, it doesn't have electrons, it's lacking in electrons, the chlorides will donate their electrons. The electrons from the chloride will be donated and they will travel this direction. Okay, E minus, E minus. They will travel, and you can see here that we're going to have an electronic circuit or electrical circuit. So the electrons come down here. Obviously you have a surplus of them now in the negative cathode, and then the sodium will pick them up. And then chloride will do that again, and we have electrons moving all the way around the circuit like this. And so really, you are giving an electron from the chloride to the sodium, but the way that you do that, in order to not form a bond between the sodium and the chloride, is via the electrodes. And so obviously, at the positive anode, the chloride ion will turn into a chlorine atom, and two chlorine atoms are going to form a chlorine molecule. Chlorine is gas at room temperature, and so this is what our equation will look like. Chlorine minus will form chlorine atom plus an electron, because it will give away an electron and produce the chlorine atom. If we wanted to be complete and talk about this in terms of chlorine molecules, which is how you're going to see them because a gas will be given off, then that is Cl2. And so to balance, we need two of these. Two chloride ions will form one chlorine molecule, and that will give off a total of 2 electrons, because one from each of the ions. In another video, we'll have a look specifically at how we use electrolysis in extracting copper. But for now, please comment below if you have any questions, and I'll see you in the next video.